Hey, AP Chemsters, this is Mrs. Vanderwall bringing you Blankwalle section 5.8 part 2. And so earlier in this section, we're talking about the kinetic molecular theory. And I made kind of a little big deal about kinetic energy equals 1/2 mv squared, m being mass and v equals velocity in this case. Note that a little v is velocity and a capital V would be volume, so we're talking about mass and velocity. And I said that the lightweight molecules are going to go faster and the heavier molecules are going to go slower. And this section and section 5.9 is actually going to talk about that a little bit more. Okay, so this is distribution of molecular speeds. And I noticed Maxwell's equation kind of here in the middle of your screen here. And don't worry about the Maxwell's equation. This formula is not on your equation sheet. If needed, they'll be given to you. My guess is that the AP probably won't ask you to calculate this anymore. They used to, as a matter of fact. But I think what they will be more likely to ask is interpretation of some of these graphs here. So if we are to look at this graph, this is a graph of the Maxwell, I think it's Boltzmann distribution. And what does this mean? Well, let's look at the axes of it. So the y-axis is the relative number of nitrogen molecules with a given velocity. And notice what else you see. So these are all the exact same molecules. And notice at different temperatures, they have a different distribution. Okay, so it says changing the temperature affects the shape of the curve, not the area underneath it. So if you were to analyze it using maybe some calculus there and do the area under the curve, you notice that each of these curves are going to actually have the same exact area. Okay, and so that's going to be consistent throughout here. The change in the number of molecules, and then all bets are off. I mean, if I have 100 molecules in the first curve at 273 and 500 molecules, then you can't really compare them. And what this does is Maxwell equation right here is the root mean square. That's what this U means, is the root mean square. And what is a root mean square? It's actually an average velocity. And if you look at it, there's a lot of calculus really involved if you study this equation a lot more. The 3 in the equation actually means, like, for 3 dimensions here, that what is the distribution. I really wouldn't get hung up over this. If you're doing some calculations, actually do a couple below. You're going to use a different R value. If you look at your equation sheet, notice they will give you 3 different R values. We use 0.0821 a lot. I don't use the one with torr in it, but they're the other one with joules, and we're going to use this one quite a bit throughout the year too, this 8.3145. Notice the unit is joules per Kelvin mole, and because it's an energy, like this is tied in with kinetic energy, we use the one with joules, which is a unit of energy. By the way, chapter 6, we're going to delve into that a whole lot more, what a joule is. So just for right now, by the way, it's Joule. It'll be a joule there. So anyway, let's go back and look at this graph here, because again, that's what my guess that they'll have you do in this section, if anything, is analyze this graph and what does it mean. So over here, what's going on? We have a high peak at 270 with 273, which is a lower temperature. So what does this tell you? That my y-axis is the relative number of nitrogen molecules. There is a lot of molecules of nitrogen, around maybe like 250 or 300 meters per second velocity, and they're all bunched together. All right, and as you warm up, the molecules have more and more a variety of velocities. That we still have a peak here at around, let's say, 1,000-ish, but you have more that are going faster and more that are going slower. And as we heat it up even more, we have a peak maybe around 1,500 or maybe 1,300, something like that, at a higher temperature. But again, they're all spread out. So this is what I would like to make an analogy of, okay? So if I go, hey, AP Chemsters, let's walk down to the closest gas station and get some ice cream down there. I think UDF is a little far away. And So we're just going to walk down there. So our speed is kind of slow. But when we walk together, we can walk in a big group. We can all pretty much stay together. And that's what's happening here. At a low temperature, meaning that we're walking really slow, we can work together as a big group. And so that most of us are going at the exact same velocity. So we can just meander as a group with the same speed. So then we go get our ice cream, and maybe we're talking and having a good time, and then someone looks at the watch and says, oh, golly gee, we need to get going. We're going to be late to our next class. We need to run back to Oak Hills. So now what happens? We're all going, as a group, faster. But what happens? Let's say this black line here is us running back. So we're running, so the temperature goes up. But what happens? We have some speedsters that are going to get back to the high school really, really fast. Maybe the guys and the ladies on the track team are way up here. And then the majority of us are going to be here. And well, actually, this is probably Mrs. Vanderwalle down over here. Okay, I'm not going too fast still. Even if I'm supposed to run, I don't run real fast. Okay, so we become all spread out, and we're going to elongate our group. It's not all huddled together. We're a lot more spread out. And that's what's going on here with the distribution of temperature and velocity. So what is the summary of this graph? The hotter it is, all right, the fewer molecules are at the average speed, all right? You are more spread out. The colder it is, the more grouped together these molecules are, and more molecules can stay at that, the average speed there, okay? So what is that average speed? And that's what this root mean square is going to tell us, okay? So let's look at problem number 36. Let's actually calculate what this average velocity is. So it says calculate the root mean square velocity, or the average velocity for the atoms in a sample of oxygen gas at 25. So I need to take, here we go. So the root mean square is the square root of 3 is a constant. Here's this 8.314 joules over mole K times the temperature, 298 Kelvin, I guess I left out my unit, divided by the molar mass. So why don't you get out your calculator and plug away and see what you get. Take a few minutes out and come up with an answer. All right, what did you get? Did you get a 15.2? That's what I got. Remember, this is for oxygen. So rewrite down O2 right here, because please humor me. Do this for me. Over on this part, will you find the root mean velocity for, let's say, nitrogen? Go ahead and do nitrogen gas, N2. Go ahead and take your time and plug in the numbers and see what you get. So pause this. All right, welcome back. Let's see what you got. Well, again, this is for nitrogen, right? Notice I have 28 grams per mole down here, and I have 16.2. So once again, what does this mean? I'm comparing two different gases here, and that's going to help us down below. So just humor me and look at those two numbers in a minute. So problem number 37 says, here we go. We have 3 identical flasks. So we have flask A as carbon monoxide at STP. Flask B is nitrogen at 250 torr. And flask C is hydrogen gas at 100 torr at 0. So notice that they're all at 0 degrees. So it says, in which flask will the molecules have the greatest average kinetic energy? Remember what we said about kinetic energy. Kinetic energy is proportional to temperature. So the greater kinetic energy is at the higher temperature. It makes no difference what molecule it is, what kind of gas it is. Remember I said that earlier when we were talking about kinetic molecular theory in the last part of the set, or the first part of this section 5.8. It makes no difference what gas we're talking about, okay? And that's the same thing here. The average kinetic energy is only related to temperature, not the identity of the gas. So what would be my answer here, okay? If they are at the same temperature, then they have the same average kinetic energy. So none of them do, okay? Now remember, there is a difference between kinetic energy and velocity, okay? So remember what I said earlier, the larger molecule goes slower. The lighter molecule goes faster. Okay, so what will be your answer here? Well, let's see here. I wrote, if kinetic energy is the same, why? It's the same temperature. Okay, that's what's going on here. So kinetic energy is the same, but if the velocity goes up, that's what they're looking for, is the greatest, mass goes down. So which one has the lowest mass? Well, your answer is flask C. Please, please know. I know I've been teaching AP for a long time now, okay? Students will mix these up. Learn these definitions. Star this. Circle this. When you study your notes, study this, okay? I promise you there'll be some kind of question on your Chapter 5 test dealing with the difference of these two. What great multiple choice questions these would make. So I'll say it once again. Kinetic energy deals only with temperature. So whichever temperature is the highest has the greatest average kinetic energy. But what is kinetic energy was 1/2 mv squared, and that v is velocity. So now, which one will have the greatest average velocity? The one that is the lightest. So go back up here, okay? Which one has the let's say the highest average velocity there? The one that is the lightest. So here's oxygen at 15.2. There's its velocity. And here is nitrogen. Remember I had you do that. Here's nitrogen's average velocity at 16.2. So look what happens. This is why I wanted to do nitrogen. The lighter the gas, the faster it goes. The heavier the gas, the slower it goes, okay? So make some note, jot that down, write it down, highlight it, do whatever you need to, okay? So hopefully you understand what I'm just saying here. All right, so we are right here, and let's see here, variation of the velocity distribution with molar mass. Let me put this back down here. I may need to make this bigger. Hang on a second. Okay, so look at what's going here. This is the variation of velocity distribution with molar mass, okay? So what does it say? Relative numbers of something, I can't even read it, with something and velocity. I really can't read it. What you need to see about this page here, okay? So this graph, you're at the same temperature. Okay, did you write that down? These are all at the same temperature, maybe at 293. I have no idea what temperature, maybe it's 273. I don't think it says. But so just know they're at the same temperature, so they have the same average kinetic energy. Okay, but look, the heavier molecule, oxygen, all right, has the lowest average. The hump, the top of the peak here is the average. So oxygen, the heaviest one listed, has the lowest molecular speed. Nitrogen is a little bit lighter and it goes a little bit faster. The average, that's the top here. Look over here at hydrogen. This kind of looks like it's the peak, if you will. All right, notice that the average velocity is the greatest. Why? It's the lightest gas. Okay, so this is the variation of velocity distribution with molar mass. So what does this graph tell me? That the gas that is heaviest has the lowest average kinetic energy. The gas that is lightest has the greatest average, or has I'll say it again. The gas that is lightest has the highest average velocity. I almost said kinetic energy. That would have been incorrect. They all have the same average kinetic energy if they're at the same temperature. Okay, so let's see. This is what down here is saying. So they are at 25 degrees. I just didn't see this. So it's at 298. So at a given temperature, there is the distribution of velocities among the particles in a sample of gas. The exact shape and peak of the distribution varies with the molar mass of the gas. Okay. So I'm going to leave you here. This is the end of section 5.8. So don't wait to be great. We'll see you next time. Bye-bye.